Director anymore. Not anymore. That's Claire Max's job. And, in fact, I was making a point with this first slide, the crisis at Lick Observatory. That was my talk back in May of 2014. And the title of my talk today is The Future of Lick Observatory, Look at the Frontier and How You Can Help. And the difference, going from crisis to a future, reflects the enormous change in our funding situation and our scientific planning, morale, everything associated with the observatory. We've gone in the space of about a year from a place where our survival was in doubt to a place where we're very confident now we do have a future, and I'll be explaining some of the great things that we're doing. How is the sound here? Can people hear what I'm saying?
Higher.
Higher, okay. So turn up the sound so that the folks in the back can hear. Is that any better?
Yes, thank you.
Okay, great. So, I'm taking you on a roller coaster tour here with over 100 slides. We're going to move very, very fast, but I thought you would like to see a lot of pictures. And here's the first one. UC owns and operates Lick, which is on Mount Hamilton, California, 10 miles east of San Jose in the Coast Range. There are a lot of telescopes there. I'll be telling you more about which ones we use for research. The history goes way back. 100 and, gosh, what is it now? 27 years, I guess. 28 years almost. A gift of $700,000 back in the day from James Lick, a very eccentric guy, an early pioneer in California, very wealthy, probably, certainly the wealthiest guy in California and one of the wealthiest people in the United States at that time. So that gift of $700K, if you scaled it, not by inflation, but as a fraction of gross domestic product, in other words, the percentage of national effort, that gift would be $1.2 billion today. My point being it's very sizable. And in fact, it was the biggest gift in the history of science in the entire world up to that time. And what it made possible was the world's largest telescope, this wonderful 36-inch refractor, so scenic, so beautiful. And it also bought him a tombstone. Here lies the body of James Lick at the base of the pier of the 36-inch. So here are some photos of Lick Observatory from the early years. 1888, that's when it went into operation. There's, no cars, no electric motors. Everything was done with other forms of power, including horses. This was the first telescope, a beautiful 12-inch refractor, which is now in storage. And here's a picture of the main building. So it's quite a story to explain how this wonderful telescope was built with the technology of the day. It's a jewel of 19th century high technology. For example, look at this floor here. It rises up and down a total of 16 feet, which is necessary in order to be able to stand at the tailpiece of the telescope in all orientations. How do you raise a floor that weighs 59,000 pounds with no electric motors and so on? I'll let you ponder that, and maybe we'll have a guessing game at the end of this talk to see who can figure that out. So this was the world's first modern mountaintop observatory. Observatories were in cities where they were convenient. This was not convenient. This was a 2-day ride from Berkeley. You got on the train, you went to San Jose, you changed teams 3 times, you slept overnight in a hotel in order to get to the top of the observatory. And many people did that. It was a real tourist attraction despite the difficulty. But more to the point, this is really the first big science project in the history of the world, and it was the big science project that was the entree for American science. Back in that century, the late 1800s, it was German and English universities that dominated science. And American universities were literally nowhere in science. But we had one thing in America that Europe didn't have: clear skies. And so we proceeded to build great observatories. Lick was the first, Mount Wilson was the next, Palomar, Kitt Peak, etc., etc. And gradually we stole science away from the Europeans, and this was the first beachhead for doing that. So there were many technology firsts that were invented at Lick Observatory. For example, perfecting the modern reflecting telescope, which started in about 1895. a balky telescope here that wouldn't point, etc. It was collected light with a mirror, not with a lens. The refractor used a 36-inch lens. This is a 36-inch mirror. And this was the wave of the future for astronomical photography. These were cutting-edge, unbelievably interesting forefront pictures that were taken at the time. Nobody had ever been able to take pictures of galaxies before. And as a result of these pictures, the universe of galaxies was uncovered and the vastness of the universe was discovered also. Okay, moving on, a great discovery in 1922. Almost nobody knows this. The proof of general relativity was carried out by a team of scientists from Lick Observatory. Usually credit is given to Arthur Eddington and an eclipse expedition in 1918, I believe, but in fact, his data don't stand the test of modern analysis. He had only a 2 sigma result. This was a 3 sigma result, and Eddington should never have published by the standards of modern science. So what people did was they went off and took pictures of the sky around a solar eclipse while the sun was blocked. And then they took pictures of the same piece of sky after the moon had moved on, the sun had moved on at night, 6 months later. And you compared the positions of the stars, and because of the general relativity effect bending light rays, you could see that stars around the sun had moved by a very small distance, like an arc second or so. And that was one of the standard proofs of general relativity, and it happened as a result of very careful measurements by our guys at Lick Observatory, getting a 3 sigma result in 1922. Here are some pictures from the expedition. Another technology first. The first lunar laser return for laser ranging in 1969. Here is the reflector, which was placed on the moon's surface, and a laser from the Shane telescope went up and bounced off this reflector. And the time of flight allows you to measure the distance to the moon very accurately, and now that is routinely used to monitor the moon's orbit. Okay, something very dear to my heart. We invented the first remotely operable digital focus in 1972. Before that, the way you used a telescope was you went there and looked through the eyepiece. Or maybe, if you were lucky, you put in a photographic plate. But now we invented here in Santa Cruz a digital detector which translated photon information into numbers, which went down to the computer, and the computer would make an image for you. So here is the spectrograph, this black structure at the back end of the Shane 3-meter telescope. And we put a TV camera on the telescope so that you didn't have to look through the eyepiece anymore. You could see stars in the TV. Here's the output. This is yours truly looking at a spectrum, which you got in real time. It was amazing. You could just see the counts build up. It was very exciting. And I even went observing when my daughter was six weeks. So easy to use, I used to say this was child's play to use this system. Okay, so lots of good things happening at Lick in the past, and lots of things in the future, but unfortunately, the Office of the President, let me remind you about the structure of the University of California, okay? The University of California has multiple campuses. Astronomy is the only program that has centralized facilities that service astronomers or scientists from many different campuses. There are 10 campuses, and we have astronomers on 8 of them, and of which Lick is one, and the Keck telescopes out in Hawaii are another. So we are governed not by a campus, but rather by the Office of the President, otherwise known as UCOP. And they're in charge of our budget. And they announced in the summer of in September of 2013 that they plan to cut off all funding for the observatory in the summer of 2018. So we were getting something like $1.2 million from them. It's very hard to raise that kind of money from private funds on a regular basis. So effectively, if they had done this, this would have been the death knell of Lick Observatory. And remember that we were in, or just coming out of a severe financial crisis, and so they were very focused on saving money. Well, they changed their position, and they changed it under pressure. So take note of the date here, March 4th. 2014, here's a letter from President Napolitano to our Congresswoman at Lick, Zoe Lofgren, from San Jose. And her letter says, the use of Lick has decreased and is now limited to a small number of individuals at just a few campuses. This was completely false. We were hosting astronomers from all 8 UC astronomy campuses, as well as 2 national laboratories, and we were using the telescopes for both education and research. So here's how the position changed just 6 weeks later, or 7 weeks later, April 29th. The president is now writing to Zoe Lofgren. The university agrees that Lick Observatory is a valuable research facility and is a resource for astronomy education. So what happened? Public attention was thrown, a spotlight was thrown on UCOP governance. First of all, our local California congressional delegation got interested, and 35 out of 40 congresspersons wrote to the UC president and urged her to keep Lick open. We had positive coverage in a lot of media, including the UCLA Bruin and the Daily Californian. There were op-eds in the San Jose Mercury and the UCLA Bruin, a story on KQED California Report, and articles in leading publications. Best of all, thanks to yours truly, the untruths that were present in that first letter from Janet Napolitano were unmasked, and they were due not to her, but to the fact that she had farmed out the writing of her letter to a senior UCOP official who pretty much had it in to close Lick Observatory. He wrote a letter to the congressman that had 9 errors of fact. It was very easy to write another letter correcting his 9 errors of fact. And the net result was that the president's office was so embarrassed they fired this guy. And that was the critical point, since when things have really started to improve. And our current director, Claire Max, is doing a brilliant job of repairing relations with the Office of the President, and things are going very well. In fact, when she took over as the permanent director, this was just announced on or about, I guess mid-August or thereabouts, she's now been promised a $2 million increase in budget. $5 million will go to $7 million in a couple of years. So there's just been a complete turnaround in attitude by the Office of the President. What is Lick good for? Well, first of all, it's vital for research. Current and future research at the cutting edge, especially for unique projects that require large amounts of time on moderate-sized telescopes. And we design new instrumentation and technology for use at Lick, but also at our other big telescopes, including Keck. So you can think of Keck as a technology test bed. I'm searching for the word that everybody, incubator, that's right, that's the word, going word for technology these days. Also, education and outreach, hands-on training for our graduate students, undergraduates, and postdocs. Our other big telescopes used by UC right now are the Keck telescopes. You may have heard that we're also in partnership with Caltech and 4 countries to build a 30-meter telescope. I'll say a little bit more about that later. Those telescopes, Keck and the 30-meter, are so big and so precious and so expensive to operate that a student, even a graduate student or a postdoc, can't get time in their own name. So if you want to educate people to do their own projects, do their own theses, plan a project from start to finish, go observing, learn how to observe, find objects in the telescope, make sure that the spectrograph is working, this is the place, Lick Observatory, where you get hands-on training. And lots of students come to throughout the University of California, those 8 campuses, in order to have access to Lick. And in fact, in just the last 3 years, we've had 69 different student PIs, and when I last checked a year ago, we had 20 PhD theses that were underway at Lick. Of course, the other big thing that we do at Lick is public education and outreach. It's really architecturally, culturally, scenically, unique Bay Area treasure. Here is a beautiful picture panorama of the main building. This is the 36-inch refractor, and this is the original 12-inch dome, which now has a 40-inch reflector in it. The interiors are elegant, and they've been beautifully kept up. Interesting. Okay. We just crashed. Let's see. Get located. Let me do that. I should know where I am.
I don't know, but it's intense. Yeah, it's really intense. The road was very interesting. The road was like your life is in your hands. Well, he was so 17. Oh, intermission. 17 with a flip. And there's not 2 lanes. It's like, this is big enough for 2 lanes. Like, where are the markers? If someone was coming the other way, you're gonna die. It's opposite from all your There wasn't enough room for 2 lanes.
Okay. This is a dangerous slide, so let's get off it fast, okay? And then in addition up there we have invaluable notebooks and archives from the observing that's gone on for 125 years, a real historic treasure trove. 35,000 visitors per year visit us. And we, especially in the summertime, we have lots of events. You're invited. Music of the Spheres concerts, summer viewing at a very reasonable price. Amateurs come and bring their telescopes and you can look through them. And we're also an event venue. Some of you are the right age. Are you thinking about getting married? You might want to rent our facilities for a unique wedding venue. So, all in all, Lick is just a place of great natural beauty and a unique Bay Area treasure. So, what I'd like to talk about for the rest of this talk is the science that we've been doing at Lick Observatory. World-leading current and future research. So, topic number 1 is exploding stars, specifically supernovae. Here's an example of a supernova that exploded in 1987 in the Large Magellanic Cloud. This is a picture of the region before the explosion, and this is as the supernova was going off. You can see how bright it was. When these things explode, they send out expanding envelopes of gas into the interstellar medium. Here's a rather young one. This guy, the Crab Nebula, went off in 1054. This is an older one, larger and more tenuous. And this process is really important for us because there's a sort of a cosmic recycling and enrichment that's going on here. Here is a supernova. It's exploding. Its envelope is going out into the ISM, and that envelope is enriched with heavy elements, which the supernova has been cooking in order to shine. What they do is they put hydrogen and helium together to make heavy things, like carbon, oxygen, nitrogen, iron, etc., the stuff that we need to make planet Earth and our bodies. And that stuff goes out into the interstellar medium, gets mixed with the interstellar gas, gets incorporated into new stars, and makes planets. And every time you go around this cycle, the interstellar medium gets richer and richer in heavy elements. So supernovae are really why you and I are here. Very important for us. In fact, here's another question you can think about for the end of the talk. All of these heavy elements in your body, carbon, etc., etc. Question is, how many supernovae were they part of? Okay, so think about that one and we can come back to that. We would like to know more about these. These are fundamental objects. They're very interesting. And there's a little telescope. We call this the little telescope that could. A 0.76 meter telescope at Lick that belongs to a professor at UC Berkeley, Alex Filippenko. And he's been imaging nearby galaxies. Here are some examples of pictures from his telescope. The arrows point to supernovae. And this is a robotic telescope. It opens automatically at night. It observes all night long. It's looking for rain and various other bad things. It finds them, it will close. Then it sends its images down to Berkeley in the morning, where they're analyzed automatically, but also by a team. He always has lots of students working for him. Great student opportunities here. And he's been conducting a supernova search. And for many years, he had the world record discoveries of supernovae from his team, reaching a peak of 95 supernovae in the year 2003. Why did he want to do that? Well, he wanted to study the nature of these supernovae. The way we do that is on a different telescope with a different instrument called a spectrograph. We put the supernova light through a prism or a dispersing element, and we get a spectrum of it. And when we do that, we find that there are two different kinds of supernovae. One of them, on the bottom, is called type 2. And that is produced by massive stars at the end of their life when they explode. And as we'll see in a minute, they're actually not so interesting for cosmology. The more interesting one for cosmology is type 1a. They are the ones that make iron. And the interesting thing about them is that they are much more uniform. They might be standard candles. A standard candle to an astronomer is an object that has predictable brightness. It's either all the same, or you can measure something about it that will tell you how it's different. And if you know that, then you know how far away they are. Once you calibrate them, get a 0 point once and for all, then you can start measuring the distances to other objects when you discover these supernovae. So people got very excited about standard candles. Why did they? Because you could use them to study cosmology. Okay, so now I'm moving off the topic of the stars themselves to their application. And the application was to detect that the universe is accelerating due to something called dark energy. So the accelerating universe, that concept goes back to the days of Edwin Hubble, who did not work for us. He worked for Mount Wilson Observatory down in Southern California. And he was the person who discovered Hubble's law, that the universe is expanding and that the farther away you look at a galaxy, the faster its velocity is. So you can take that law and you can extrapolate back in time, and everything comes together at an instant, which we call the Big Bang, or the origin of the universe. So the latest chapter in cosmology is to measure the expansion history of the universe to determine its past, but also its eventual fate. So an analogy here would be, here is the Earth and a ball is being thrown up. The ball motion away from the Earth is like the expanding universe. You could think of these as two galaxies moving away from one another. They were all being tossed apart at the Big Bang with some impetus to move them, to separate them. Will they keep separating forever, or will they fall back? The analogy with the ball is a good one. If I throw the ball faster and faster, it goes farther, but eventually turns back. However, if I give it escape velocity, it will actually escape from the Earth. And there's a relevant, similar concept in cosmology called the escape velocity of the universe. So people wanted to use supernovae to actually measure this effect. And how do they do that? Well, we got big telescopes like Hubble, and Hubble takes pictures of things that are very distant, and Hubble could discover distant supernovae. Here are some pictures there with supernovae and galaxies indicated with arrows. And then you went to big telescopes, the Lick telescope, the Keck telescope, and others, and took spectra, and you tried to figure out whether or not these objects all had the same brightness, and spectroscopic differences were found among the type 1As, and it looked as though they weren't all quite the same brightness. Now, could we fix this problem? Could we convert these type 1As into cosmic standard candles? Well, let's spend a minute talking about how a type 1A supernova occurs. Here is the Sun, Earth, and a white dwarf shown to scale. Okay. So the Sun is very big, the Earth is small. The white dwarf is the core of the Sun after it evolves. You can see that the Sun is going to leave behind this tiny core, just a few miles in diameter. So let's put a tiny core like that, a white dwarf, next to a bigger star that's still evolving. That star expands as it evolves, and some matter flows over onto the white dwarf and adds mass to the white dwarf. And there's a very famous discovery made in the 1930s that there's a maximum mass that you can put onto a white dwarf before it will explode. It's called the Chandrasekhar mass, and it's about 1.3 solar masses. And so that explains why type 1As might all have roughly the same brightness, because they're all the same mechanism and they all come from the same threshold number. But in detail, they turn out not to be quite the same. The explosion differs, and there's a range in brightness shown here. But fortunately, we can calibrate the brightness by noting that the light curve, here's time here, brightness versus time, the shapes of the light curves correlate with how bright the supernova is. If it's luminous, then the supernova has a slower light curve. So you have to measure all of that. So what's our plan here in studying supernova and calibrating them at Lick Observatory? Well, the first thing we're going to do is we're going to find nearby supernovae with this little Keck telescope. And then once we know where they are, we have to immediately rush off and get time on the 3-meter telescope to get their spectrum. And that will tell us two things. Is it a type 1A or is it a type 2? If it's a type 2, we throw it away. And if it's a type 1A, we can measure the redshift of the galaxy that it's in. And locally, we can use the redshift distance relation to tell us how far away that supernova is. And then finally, we go to the nickel 40-inch telescope and we measure the light curve. And here we have again the Filipenko student crew who did all of this kind of information and worked hard at it. So I'm talking about a period of time during the 1990s when the basic physics of type 1A was being uncovered using, among other things, data from Lick Observatory. Lick was very important for this. So here's an example of Shane spectra, that, this should say Shane spectra, not Shane light curves, that Alex Filipenko took. This is the same supernova as a function of time, and you can see how it's evolving. Its light is changing, and its spectrum is changing. He's studying all of that. And meanwhile, on the nickel, they're measuring the brightnesses of that supernova in different colors. So picture putting together data on literally hundreds of supernovae to calibrate them as standard candles. He hands off that information to other teams using big telescopes like Keck that are finding supernova in the distant universe with the Hubble Space Telescope. He tells them how the calibration works. They say, oh, thank you very much. That means for every galaxy, for every supernova I'm now measuring far away, thanks to your calibration, I can get a distance. And the other thing that I can measure is how bright it looks. And that combination of how bright it is versus an independently measured distance, that's the stuff of cosmology, and we can study the history of the expansion of the universe. And here's the result. Okay, so what is this graph? This is the distance. What does it say? Okay, this is the scale of the universe. You can think about that as the distance between any two galaxies, okay, versus time. So early on, all distances were 0 because that was the Big Bang. The Big Bang happened, things went outward, and this is the curve of the history of the expansion, possible models that the universe might obey. And there was a huge surprise in this result because of the discovery of this plateau, which nobody expected. A rapid expansion and then a temporary sort of deceleration, a static, almost static period, and then a renewed expansion. That's what our universe is really doing. This here seems to be our actual universe. What would cause such strange behavior? You only get that with something called dark energy if you put it into the universe in addition to regular matter. And so we now have a new energy budget for the universe in addition to normal matter, which is what we have here in this restaurant, and in addition to dark matter, which sounds weird, but actually isn't so weird. It's holding the galaxy together. We have something called dark energy, which is not matter at all. And it has the weird property that when you put it into a universe, the universe expands. Dark energy does not get more dilute. And if that is not crazy and ridiculous sounding, I don't know what is. It doesn't obey normal conservation laws, but nevertheless it seems to be there. And when you put it in, it causes this very strange behavior in the expansion and actual acceleration at late times. Well, this was new news. This is new physics. It's actually a new form of gravity, and it was awarded rewarded with the Nobel Prize in Physics in 2011. Science magazine called it the most interesting scientific discovery of that year. The three people who earned the Nobel Prize are these three individuals, a man here from the Hubble Space Telescope, a man from UC Berkeley, and a man from Australia. And they won the prize, but our guy, Alex Filippenko, should also have won the prize because he was the one who provided the calibration from Lick Observatory that made this work possible. All right, I'd like to move on to another completely different topic, a topic in which Lick also leads, and that is the discovery of planets orbiting around other stars, so-called exoplanets. Are there other planetary systems? And are any of them like our solar system? That's the question we're trying to answer now. So, how are we going to find them? This technique was co-invented at Lick Observatory. Some Swiss people had invented it, and at the same time, three Lick astronomers were developing it. And it's called the Doppler wobble technique. When a planet goes around a sun, the planet actually pulls on the star and causes it to make a very small orbit, and the star moves. We can't see the planet, but if we take a spectrum of the star, we can see this Doppler motion. Sometimes the star comes towards us, sometimes it goes away, and this changes the wavelength of light that we measure. So again, we need a spectrum. We need to pass the starlight through a prism, disperse it. There are all these features, dark lines in the spectrum. Here's what a real spectrum looks like, taken with a high-resolution spectrograph at Lick Observatory. And all of those dark lines that you see there are due to some element or other. There's iron, magnesium, everything that we're made of. This just proves that the atmosphere of the sun and stars are made of the same stuff that we are. Okay, so the star's motion is discerned as a very tiny motion of this whole spectrum, either to the blue or to the red. And we're getting very good at measuring these motions now. Now the accuracy is down to 0.5 meter per second. A whole star, and you can measure 0.5 meter per second. That's about the speed at which you walk, slowly, right? So the first real discoveries were made at Lick in 1995, just a few months after the Swiss guys announced the same star, 51 Peg. Here are the three Lick astronomers who built the spectrograph and developed the technique. And this is the curve in their paper that illustrates the Doppler motion. So as we go around here, this is the phase in the orbit, and this is how much the velocity is changing. The total amplitude in this star, this is a piece of cake. This is 100 meters per second. Man, that's nothing by today's standards. The technique has gotten much more accurate, and we're down to 0.5 meter per second. This got a lot of attention. Is anybody out there? Time magazine wrote in a story about the two stars. And now, thanks to Doppler measurements, but also to the recent Kepler spectrograph, the Kepler satellite, a NASA satellite which was extremely productive, we now have found, I just heard, something like 5,000 candidate exoplanets around other stars. There are a lot of them. Okay? So we're sort of beyond the task of just finding them. It's now getting more interesting, and we're interested in the habitability of these planets. Are they too hot close to their stars? Are they too cold, or are they in fact just right, sometimes called the Goldilocks effect, right? Okay, so we're now searching for habitable worlds and Earth lookalikes. Well, as we go forward on this topic, another telescope, 2.4 meter automated planet finder telescope at Lick, is going to play a major role. Here is the 2.4 meter next to the Shane 3 meter dome. It's an amazingly compact and efficient little telescope that fits very neatly into this very small and compact dome. The secret weapon is the Levy high-resolution spectrometer, donated by Silicon Valley guru Kenneth Levy and his wife Gloria. They paid for it, and it was designed and built at Santa Cruz here by Steve Vogt, an astronomer at UCSC. And this is the spectrometer which has now gotten to 0.5 meter per second. And it's now, along with one other spectrometer owned and operated by the Swiss fellows, it's one of two of the most sensitive Doppler spectrographs in the world. Okay, so what are we doing here? This spectrometer is now systematically surveying the nearby stars. Why are we doing this? Because they're the closest ones. If we discover interesting planets, then they're going to be nearby and it's going to be possible to actually observe them. We're to the point where we can study and discover multiple planets in one of these systems, but in order to do that, you have to watch them for years. You'll see phase due to one massive planet, you subtract that away, you see residuals due to the next planet, and you can get down to very, very small objects this way. Approaching Earth masses, but not quite. There is a major satellite that's scheduled to go and look for transits of these planets, and our goal with the APF survey over the next 10 years is to locate all candidates amongst this local sample that TESS will test for exoplanet discoveries. So there's just an endless number of stars that need to be looked at and followed very carefully and modeled. This is a very long, this decades-long program, so you'll have to stay tuned as we get the data at APF. The last topic I'd like to tell you about is adaptive optics, another area where Lick Observatory has led. Specifically invented something called the laser guide star adaptive optics. So why do we need adaptive optics on ground-based telescopes to make sharper images? Well, this is an area of the Hubble Deep Field taken with the Hubble telescope, but blurred as though it were seen with ground-based seeing. And this is what the actual field looked like. So the difference there is showing you what the effect of ground-based seeing is like. And we'd like to undo that. It costs billions of dollars literally to put the Hubble telescope up in orbit. Can we do that with our ground-based telescopes for a lot less money? That's what adaptive optics is trying to do. So here is how adaptive optics is working. There is light coming in to the telescope. Move a little bit so that I can use my laser pointer. Light coming into the telescope from a star, and it's aberrated, as indicated by this wavy wavefront. The wavefront should be nice and straight. They're not because of the atmosphere. It's distorted. And it goes into the system, and there's something here called a wavefront sensor, which actually measures these distortions. And information goes back and runs something called a deformable mirror, which is bent in such a way as to exactly undo the wavefront distortions. The only trick is that you have to do this 500 times a second. So you have to measure what's wrong with the wavefront, and then you have to correct it 500 times a second. Aside from that, it's easy, okay? Okay, so now here's a demonstration of how that can work. Let's see here. My movie didn't load. Sorry about that. Click where? That's what I'm doing. No, I'm not getting any movie icons, so I think it's not working. Okay, I'm very sorry about that. If it were working, what you would see is this image here dancing around, and that's the image through the 40-inch telescope with no adaptive optics turned on. And over here, this very nice, small, tight image is the same star with the adaptive optics unit turned on. So this gives you a feeling for the level of improvement that you can get if you have a working adaptive optics system. Now, there's a trick here, though. You need information about that wavefront. And one way to get that is to look at a nearby star. Stars are supposed to be sharp, and if they don't look sharp, well, you can see in what way they're not, and you can use that information to fix them. But unfortunately, only 1% of the sky has stars next to it that are bright enough to use that way, so you have to make your own star. And that's where Lick Observatory comes in. It was actually Claire Max, our director, and two other people who invented the concept of the laser guide star adaptive optics. This is using a laser to make a star, and it was pioneered. The first telescope that used this was the Shane 3-meter at Lick. It later became the basis of laser guide star adaptive optics at Keck. And here you see the laser coming out of the Keck telescope. So how does it work? Well, you take a laser beam and you shine it out of the telescope and it goes up into the atmosphere. But 90 kilometers up, there's a layer of sodium atoms, and they are sensitive to sodium D light, which is exactly the color of this laser beam. You excite those atoms, their electrons go up one level, and then very rapidly they decline, and that causes those atoms to glow. And so in that layer, you can create a little glowing star by shining just exactly the right wavelength on it. And the nice thing about this star is it's like this laser, okay? This laser is following me around. Imagine I'm a telescope, okay, with a laser on me. Everywhere I look, this sodium layer fills the whole sky. So no matter where I shoot the laser, I always find sodium atoms. It's wonderful. So here's an example of adaptive optics on the Keck telescope. This is a moon of Jupiter called Io, famous for having lots of sulfur volcanoes on it, and this is what it looked like when adaptive optics was turned on. This is Uranus, and again at Keck, and this is what it looked like when adaptive optics was turned on. These pictures from Keck are sharper than Hubble, so it's a wonderful technique, especially on big telescopes. Here is a picture of the galactic center, which people like to study because there's a black hole there. You would like to measure its mass by seeing how stars move. Unfortunately, you can't see the stars very well, but when you turn on adaptive optics in the galactic center, now you can see the stars and measure their motion. So it's really great. We are continuing to pioneer adaptive optics technology at Lick Observatory. We have a new Shane AO system. It saw light about a year ago. It's working very well. Here is an image with no AO turned on. This is the image with the AO turned on. See the star shrink in size and get a lot sharper. And here's an image of a star cluster with and without AO. Now, adaptive optics is really the wave of the future. Why? Because Hubble is going to come down in not too distant future. It won't last forever. And furthermore, the power of a telescope, the innate power, is bigger when its diameter is bigger. What we say is that the sharpness, the innate potential sharpness, jargon word, diffraction limit, of a telescope is inversely proportional to the diameter of the primary mirror. And we can make telescopes on Earth that have diameters that are a lot bigger than Hubble. Hubble is only a 2.4 meter mirror. That's even smaller than our Shane 3 meter. The Keck is a 10 meter, and we're planning to build a 30 meter telescope. So that 30 meter telescope is 12 times larger in diameter than Hubble. We'll see 12 times sharper, and that will translate to a sensitivity for stars that's 100 times fainter. In other words, the advance of using AO on the 30 meter telescope over Hubble will be comparable to the advance of Hubble over ground-based telescopes when it went up. So Lick is very important. We have 5 or 6 new gadgets that we're trying there in order to improve AO. And over the next couple of years, we'll be developing new technologies that will translate to the 30 meter and to Keck. So stay tuned. High-resolution astronomical imaging is going to come back to the ground, and it's going to produce pictures that are absolutely stunning. Okay, so the moral of Lick Observatory is that it's very high value per UC dollar. The annual budget there's only about $2 million per year out of a total UC astronomy budget of $20 million. So it's not much money, just 10% of the total. And with that money, you buy 80% of all of UC's telescope observing nights. The other nights are at Keck, but we don't have that many nights on Keck. So if you have a project that can be done on a modest-sized telescope, Lick is your place. Furthermore, we're acutely sensitive and desirous of getting new revenue, and there are several new sources that are coming available. Because of our new instrumentation, this APF spectrograph, and, for example, the new Shane AO, we're getting interest from other observatories who want to rent our telescope time. And that's going to bring in several $100,000 more of revenue. There is a project called Breakthrough Listen, which is going to look for signals, alien signals from extraterrestrial life. And we also got a Google gift that's very substantial. Let me tell you about those two things, okay? Breakthrough Listen, there's something called the Breakthrough Foundation, which was founded by this fellow Yuri Milner, who is a Russian entrepreneur. And what he likes to do is set up efforts that are just over the top, completely bigger and better than anything that has been done in that field. And he's chosen SETI, the Search for Extraterrestrial Intelligence, as one of his fields. So recently, just a few weeks ago, the Breakthrough Listen project was announced. And here's the press conference. Here's Mr. Milner standing up there. Stephen Hawking is backing this project. Martin Rees, a famous man named Frank Drake, who pioneered SETI. And last in line, but not least, is Jeff Marcy, who is one of the users of the APF telescope at Lick Observatory. He's a Berkeley professor. So Breakthrough Listen is going to spend $100 million on radio telescopes. But oh, by the way, probably the most sensitive way of finding an extraterrestrial civilization is not with radio waves, but is with light waves. And here's a remarkable fact. I actually once calculated this myself. Let me see if I can read it to you. Okay. It's going to search for continuous laser signals that might be aimed at our solar system from specific stars under study. And the amazing thing is that a 100-watt laser can be detected. If they had one at the nearest star and were aiming at us, we could see that with a 3-meter telescope. Isn't that amazing? Lasers are incredible objects, right? So it doesn't take that much power. Now, the problem is you can only look at one star at a time or communicate with one star. Are they aiming at us? Well, who knows, right? But Jeff Marcy on the APF is taking spectra all the time for the Doppler purpose, and the laser will produce, if that star, while he's observing it, is producing a laser signal, that will be visible in the spectrum, and he proposes to look for that. So we're augmenting the Doppler search with the laser, with the Breakthrough Listen study as well. Then the last thing I wanted to talk about here is the gift from Google amounting to $1 million. It says here to relieve funding woes. I wouldn't say that that is exactly what it's for. It's an amazing gift. There are no strings attached. They didn't say what we had to do with it. They just said, we believe in you, and we're going to give you $1 million, and tell us tomorrow, but not today, how you're going to spend it. So now that Claire is the permanent director, she's able to think about the strategy for spending this money, and I think we're going to do something very exciting with it. Okay, the Lick future. Let me just summarize what I told you. Inventing adaptive optics for Lick, Keck, and TMT. Finding the nearest Earth-like planets with APF. The Breakthrough Listen project, searching for alien SETI signals with lasers. Something I didn't talk about, using those large amounts of observing time available on the 3-meter, we're going to start treasury programs, which will include mapping the anatomy of black holes, making an adaptive optics picture gallery of nearby galaxies with a resolution exceeding Hubble resolution. And there are a couple of big projects to find variable stars, exploding stars, gamma ray bursts, etc. All of these need spectroscopic follow-up, and we can do that with the Shane. Finally, there's evidence from our AO system that our site is really an excellent site with intrinsically beautiful seeing. Unfortunately, when you look at images taken with the telescopes in our domes, they aren't that sharp. And it seems as though we're probably degrading naturally good seeing by having domes that were designed and built decades ago, not using modern technology to make thermal models of the domes, etc. And so we need to conduct a site survey of the mountaintop to find out what the real seeing could be. And if it is as good as AO says, then our site would warrant a complete rebuild, tear down the Shane 3-meter telescope and do something much bigger like an 8-meter infrared telescope. What can you do to help? we've started something called the Friends of Lick Observatory. You could join. All you have to do is Google that. Go online. Even better, you could give it as a present, a membership present. Christmas is coming. I'm sure that the members of your family, especially the younger members of your family, would love to be a friend of Lick. You can send letters to the Office of the President, telling them how wonderful this speech was and inspiring it was, and how strongly you feel about needing to continue to run the observatory. Think about who might make major donations. It's amazing where these tips come from. Email us. Think of all your friends who might be swirling away money under their mattress for years and years. And visit Lick, especially in the summertime, with Music of the Spheres and the viewing programs. Whatever, we welcome your advice, and we're getting email all the time from Friends of Lick, so that's a good avenue. I'll close with our logo, Friends of Lick Observatory, and invite you once more, please join. Thank you. So I gather we're going to have a question period, is that right?
Yeah,
okay.
About 15 minutes for questions, yeah.
Okay, great. Yes, ma'am.
You're so enthusiastic about the topic, so how did you get interested in this really high level of astronomy?
You know, the question was, how did I get interested in astronomy? I was a science geek as a kid. And so I kept a weather log, and I had a microscope, and I would look at little stuff swimming, you know, from pond water. And but I always just loved astronomy. I never had a telescope. I had a pair of binoculars. I would go out and sit, lie on the lawn, Cleveland, Ohio, hot summer nights, and just look up at the galaxy. And I just loved it. And when I got to college, I deliberately chose Swarthmore College, which had a small observatory. And then I thought maybe it was chemistry or astronomy, and it turned out I hated chemistry labs. And I really liked sitting in a dome at night, thinking as I was observing, is anybody looking back at me? And so I was just hooked. Yeah.
So I remember you had said when the universe was decelerating and then it started to accelerate.
Yes.
And there was then in the Y, and it was dark energy.
Yes.
Does that mean that there was no dark energy before when it was decelerating?
Excellent question. So in the early part, going back to the curves that I showed, there's rapid expansion, and then it's slowing down, that is illustrated by the curve. Okay, like the ball slows down when it's pulled back by the Earth's gravity. So if that had ensued, then the universe would just have recollapsed. But dark energy kicked in with its outward repulsion. I should have said dark energy generates repulsive gravity. It's a really new kind of gravity. So we were on the verge of collapsing, but no, just at that moment, interestingly, the repulsion kicked in and we began to accelerate outward. Yes, so the question is why then? And the answer is hidden in what I already told you. It's due to the fact that these two components, ordinary matter and dark energy, one dilutes and the other doesn't. And so the attractive gravity is coming from the diluting component, the ordinary matter, which is getting less important with time. The dark energy was always there, but it didn't dilute, and its repulsive gravity was always constant. So it was overshadowed by the attractive gravity early on and only came into its own recently. It's